So this is going to be based off of some recent work that I've done. But the way I wanted to organize this was to spend about half of the time just introducing the model and describing the connections and existing results about it. So the models I'll talk about come from random matrices. And I'll be looking at some additive random matrix models and some quantized analogues of these things, which I'll get into. So the first half will be less focused and more for the purpose of giving you a sense and an idea of what these models are and what kind of results there are. And then the second half will transition and focus on the specific problem of studying local asymptotics at the edge. And we'll look at a specific situation where the Airy point process arises and give you a sense of some of the ideas behind the proof. And this will be a very integrable probability-based approach. Okay, so I'll introduce the model now. So let's start with the random matrix model. What we'll care about is the setting where we have k independent random matrices. These will be n by n, Hermitian matrices. And we'll specifically request that the AIs have the following structure. So we'll have lambda to be a deterministic real diagonal matrix. So these will be the eigenvalues of the A sub i's. And we want to conjugate by a Haar unitary matrix U sub I. So in other words, these A sub i's are matrices, random Hermitian matrices that have deterministic eigenvalues determined by the diagonal entries of lambda. And the eigenvectors are positioned sort of generically. So this, these A sub i's are in particular unitarily invariant. So what I mean by unitarily invariant is that if I take a matrix A and I conjugate it by some unitary matrix, that the distribution remains unchanged. So these are just unitarily invariant matrices that have deterministic eigenvalues, the A sub i's. Okay, so for this first part of the talk, I will care about the spectral measures of these random matrices. So given a random Hermitian X with eigenvalues x1 through xn, we just say that the spectral measure mu sub x is an average over the taking delta masses at the x sub i's, the positions of the eigenvalues. So the way I want, one way to picture this is, if we have x has eigenvalues at -2, 1, and 2, we're just going to put a mass of 1/3 on top of each of the positions of the eigenvalues. And this is, you can think of this as some sort of random histogram, or, if the eigenvalues are random, this is some random histogram. Okay, and what we'll do is study the eigenvalues of the sum, the sum of the AIs as n tends to infinity, where we'll have some assumptions on these A sub i's. So before I continue, I'll just pause and see if anyone has any questions about the model. Okay.
So you will be assuming k is fixed, or you will be taking k as a function of n as well?
Yeah, so k will be fixed. We want to think of k as fixed.
Okay.
But the matrix size will be tending to infinity.
Mm-hmm.
Okay, cool, thanks. So the first result I want to talk about is the law of large numbers for this model. So what this says is, okay, well, we'll assume that k is equal to 2 for this example. So we just have 2 matrix summands. And we will assume that the spectral measures of A1 and A2 both converge weakly to some deterministic mu1 probability measure mu1 and some deterministic probability measure mu2 as n tends to infinity. So in other words, in this example that I have in blue, if you assume that A1 has about half of its eigenvalues at -1 and the other half at 1, then the spectral measure of A1 will converge to this mu1 here, which is just a delta spike with mass 1/2 at -1 and a delta spike of mass 1/2 at 1. Yep. Sorry, did someone have a question?
No,
Okay.
I think it was just.
Okay. And so, yeah, so for this particular example, you would have convergence to this type of mu1. And you could also have some more complicated distributions. So you could have mu a2 with a more complicated distribution on the eigenvalues so that it converges to this shape here, which is the arcsine law. Okay. So now what you can ask is, what happens to the spectral measure of A1 plus A2? How do the eigenvalues distribute? And the answer, so just to be clear here, mu A1 plus A2 is going to be a random measure. And this will end up converging weakly in probability to some measure, which we denote by mu1 box plus mu2. So what is this box plus? So this box plus is called the free additive convolution. It was discovered by Voiculescu in 1986, and the connection to random matrices was made in 1991. And it is, for our purposes, we could just think of it as a measure on probability, as an operation on probability measures, which is going to be commutative and associative. So what this is really saying here is that if we assume weak convergence of the spectral measures of each summand A1 and A2, that we can conclude that the spectral measure for A1 plus A2 will converge to something related to this free additive convolution. I'm not going to define exactly what this free additive convolution is, but one way you can sort of define it, you can look into the details if you're interested, is there's a notion of free cumulants. So these are related or analogous to the cumulants that appear in classical probability. And you can consider some generating function for the free cumulants. So associated to some measure mu, you can look at its free cumulants, and then there'll be a generating function R mu called the R function of mu. And if you take the sum of the R functions for mu1 and mu2, this will be the R function for some measure, and this measure is the free convolution of mu1 and mu2. And this is sort of analogous in this world of free additive convolution, where this is analogous to the fact that the log characteristic functions for the sum of two independent random variables will just split into the sum of the logs of each of the summands. Okay, so any questions about this? Okay, so more generally, the statement is as follows. So we had k summands, A1 through AK. If you assume that the spectral measures of the A sub i's converge to some mu sub I weakly as n tends to infinity, then the spectral measure for the sum of all the AI's will converge to the free additive convolution of all these limiting measures. Yeah, so this result basically just extends for all k. And there is some fluctuations result as well. So I'm not going to give any explicit results here, but basically you can show that the fluctuations from this limit shape are given by some Gaussian random variable, and this can be shown by second order freeness. This was shown by Kalan, Mingo, Schneadi, and Spiker back in 2007. And also there's some other integrable probability approaches using multivariate Bessel generating functions due to Gorn and Sun more recently. Okay, so this is the first bit of the story that I wanted to say, and this is the random matrix side of the story. I will transition now to sort of the quantized analog of all of this. So here, instead of matrices, we'll be looking at representations of the unitary group of degree n. So U of n. This is the space of unitary matrices that are n by n. And we'll be looking at an analogous picture where instead of eigenvalues, we'll be looking at signatures. So signatures are just n tuples of integers, which are weakly decreasing. And we'll denote the set of all signatures by GTN. And it is well known that the irreps, or the irreducible representations of UN, are indexed by these signatures. So to introduce this model, we need some notation. So if you have a representation V of UN, this will decompose into its irreducible representations, or into the irreducible representations of UN. So C lambda here is just the multiplicity of V lambda. In other words, C lambda is the number of copies of V lambda in V. And from this, we can then define a measure rho V. So rho is just taking as input this representation V, or indexed by V. And this will be a measure on signatures, defined so that rho V lambda, the weight of lambda, the probability of observing lambda is going to be equal to this quantity here. What is this quantity? This is just saying this C lambda dim V lambda is just the dimension of the dimension contributed by the copies of V lambdas here, right? So each V lambda has dimension dim V lambda, and we have C lambda copies of it. We divide by the total dimension V. Another way, another way you could think of it is, or another way to say it is that the probability observing lambda is equal to the proportion of the dimension of the isotypic component corresponding to lambda in V. So this is the definition for these quantized models. I'll try to link this with the random matrix model in just a moment, but are there any questions about this definition so far? Okay, so let me try to further explain this analogy. So before we had some random matrix A, some unitarily invariant random matrix with deterministic eigenvalues given by the diagonals of lambda. So here instead, the analog of these deterministic, these matrices with deterministic eigenvalues are the irreps of the unitary group. So V lambda. And here, just as you had some n tuple of real numbers associated to A, given by the eigenvalues, you'll have an n tuple of integers, the signature, associated to this irrep. And it'll turn out that the operations of tensor products and matrix sums are somehow analogous to one another. And this connection here, right now it seems a little tenuous. I'm just saying, you have some n tuple here, you have an n tuple here, you have some ambient object here and an ambient object here, and some operations on both sides. But you can make this connection more precise by taking what's called the semiclassical limit. What this does is it takes these discrete models. It takes the sort of mesh parameter, the parameter that makes this thing. We have these things living in Zn, the signature, and so if we take some parameter which sort of shrinks the mesh size to 0, this will take you to the random matrix world. So let me expand on that a little more. So what exactly is this semiclassical limit? So suppose we have two irreps, V and W of Un. And right now what I want is to think of n as fixed. But we will have these representations depending on epsilon, some parameter epsilon, which I'll send to 0 in just a moment. So, associated to V, we have a signature lambda V, and associated to W, we have a signature lambda W. And we'll assume that we have the following convergence. So we'll take lambda v, so this is sitting in Zn. We'll multiply it by epsilon. So now it's sitting in epsilon Zn. And here v, again, is varying with epsilon. So we'll assume that if we take epsilon to 0, I didn't write this. Maybe I should say epsilon goes to 0. So assume that as epsilon tends to 0, these rescaled signatures should converge to an n vector, a1, an, a1, a2, an, where the entries are non-increasing. And similarly, we'll require that epsilon lambda w converges to this n tuple b1, bn. That was not what I wanted. Sorry about that. Okay. So if we assume this, okay, it's gone, but we've taken a limit epsilon to 0. And we take AB to be independent, unitarily invariant Hermitian random matrices. So these are just random matrices with eigenvalues A1 through AN and B1 through BN respectively. Then it'll turn out to be the case that if we take lambda distributed as rho V tensor W, then rescaling this signature lambda by epsilon will give me the eigenvalues of A plus B. So let me repeat that. That was a little quick, but if we assume that the signatures associated to V and W as epsilon tends to 0 converge to these n tuples A and these n tuples for the B's, then if we consider independent random matrices A and B, which have these eigenvalues, the A's and the B's, then we can identify the limit of this random variable here. So lambda is distributed as rho V tensor W. Rho V tensor W, recall, V tensor W has some decomposition into irreducibles of UN. And so we can define this rho V tensor W. And if we take lambda to be distributed as rho V tensor W, where V, recall, is depending on epsilon, so we have lambda parameterized by epsilon, then rescaling this lambda by epsilon and letting epsilon tend to 0 will recover the eigenvalues of A plus B. So that was a lot of words, but are there any questions? I can try to clarify that. Also, I'm not looking at the chat, so if anyone has questions on the chat, if someone could tell me, that'd be great. Okay, so this is the connection between these quantized models and these random matrix models. So I hope I've convinced you that there's some some sort of mesh parameter which we send to 0 that really does recover this additive random matrix model from these quantized analogues. And so now what I'm interested in is finding, asking similar questions for these quantized models as we did for the random matrix models. And so we'll consider some analog of the spectral measure. So I'll just call it the spectral measure of a representation V. And so if we have a signature distributed as rho V for some representation V, we'll define new epsilon V to be the following measure. And so here we have this extra parameter epsilon, which is really just rescaling the signature. We have this additional term n minus I. And the reason we have this is we want these particles to be to have distinct particle positions. And so if you just take a signature, we have this weakly decreasing condition, and we want to make it strongly decreasing. Okay, so we have some spectral parameter with an extra, tuning term epsilon. And now we can ask the analog of what we did for the random matrix case. So if we take V1 through Vk to be irreducible representations of Un, we have the following theorem due to Bion, Kalan, Novak, and Shinadi. So if you let the tuning parameter epsilon shrink to 0 faster than 1 over n, okay, so this tuning parameter is depending on the size n of the unitary group. And if you assume that these rescaled spectral measures converge to mu sub I weakly as n tends to infinity for each I between 1 and k, then again you will have, as before in the random matrix case, that nu of the tensor products of the V1 through Vk tuned by epsilon will tend to the free convolution of the limiting measures weakly in probability as n tends to infinity. Okay, so this result is saying that in this quantized world, if you tune these spectral measures to tend to 0 faster than 1 over n, then the limit looks just like as it did in the random matrix case. And the reason for this is that by having epsilon tend to 0 this quickly, it's basically taking a semi-classical limit while you're taking n to infinity. And so you're approaching these random matrix models as n is growing. So you would expect to see sort of the same limit. So one interesting thing that happens is that if you instead tune epsilon to be of order 1 over n, then something different happens. You'll have you'll see sort of the quantum effects. What I mean, so you can immediately see that if I were to rescale by epsilon equals 1 over n, then these strictly decreasing partitions, if it has a weak limit, this weak limit cannot possibly have density, its density cannot possibly be greater than 1 at any point. Okay, so this is, you know, like somehow if I tune epsilon to be 1 over n, you'll see that you'll sort of see that the particles can't be too close to one another. And so if you consider the same setup, so now we just replace epsilon with 1 over n, and we assume that the spectral measures of the v sub i's converge to mu I weakly as before, as n tends to infinity with this new scaling. Then the spectral measure for the tensor product of the vi's tuned by this 1 over n will tend to something that is not the free convolution. Okay, so I think I said that a little quickly, but basically this nu sub v is exactly this nu v epsilon that we defined before, but we're just asking that it tunes epsilon by 1 over n. And this theorem is exactly, you know, the assumptions are exactly the same as before, except now epsilon is 1 over n, but the conclusion now differs. So it's saying that the limit is not the free convolution of the mu i's. It is given by something called the quantized free convolution. So I'm going to cheat you out of a good definition of the quantized free convolution. I will say a couple words that so this quantized free convolution in this result, it was discovered by Buffetov and Gorin back in 2015. And you can define the quantized free additive convolution similarly as we did for the free convolution with these R transforms, where we replace these R transforms with something called a quantized R transform. So this is my sort of, quick definition. You can look in the paper of Buffetov and Gorin for additional details. But one thing I will say is that this quantized free additive convolution recovers the free convolution if you take some semi-classical limit. So if you somehow dilate these measures, you can recover the free convolution. Is there any question about this sort of set of results that I just said? Okay, so let me give you a picture. So again, so we have nu v1 converges weakly to some shape, nu v2 converges weakly to some shape, and it follows then that nu v1 tensor v2 will converge to some shape given by the quantized free convolution. And so since I cheated you out of a definition, I thought it'd be nice to give you a picture. So if you have these two limiting measures, this is what the free additive, the quantized convolution will look like of these two measures. And just as before, you can show that the fluctuations are Gaussian. This was done in a subsequent paper by Buffetov and Gorin in 2018. Okay, so let me just recap everything that I just said. So this is sort of the conclusion of the first part of the talk. So we had two models. We have this random matrix model and this additive random matrix model, and we have some quantized models. In the additive random matrix model, we said that if the spectral measures of each of the summands a sub I converge to mu sub I weakly, as n tends to infinity, then the limit of the spectral measure of the sum of the AIs will converge to the free convolution of the limits. For the quantized models, we have a similar assumption. We start with a similar assumption on the spectral measures for these irreps. But we have this additional tuning parameter epsilon, which will vary with n. So as n tends to infinity, we're going to ask that epsilon tends to 0. And if epsilon tends to 0 very quickly, faster than 1 over n, we'll see exactly the same limit as we did for the random matrix case. And if we let epsilon tend to 0 as 1 over n, then we see something different. This is some quantized analog of the free convolution. So this is the recap. Is there any questions about this part of the talk? Okay, so I will move on then to questions about local asymptotics. So in particular, we'll focus on the question of local asymptotics at the edge of these models. So here's the sort of picture, the cartoonish picture that I have for it. So we know that in the models that we have that, for example, the sums of, if we look at the eigenvalues of a sum of two unitarily invariant random matrices, that you have some limit shape. What we want to do is we want to then sort of zoom in at the edge of the spectrum and see what, we want to zoom in at a scale such that we can see the individual particles. And so for the random matrix case, this will be a scale of, we'll be looking at the scale of n to the minus 2/3. We want to describe these point processes. So the reason why we'll end up scaling at n to the minus 2/3 is that we'll be considering a scenario where the edge is described by the Airy point process, which is the limiting distribution at the edge, or the limiting point process at the edge of a large GUE matrix. Okay, so let me just say a couple words about some work that's known results in this direction. So here's a sort of non-exhaustive list of some authors that were able to obtain local edge asymptotics for additive random matrix models where one of the summands was a GUE matrix. And the reason they were able to access these asymptotics was that in the case where you have a sum A plus B, where A is GUE, the eigenvalues of this matrix have a determinantal structure. Namely, it's a determinantal point process and with an explicit correlation kernel. This is due to Brezin and Nakami, which there should be just one E here, and Johansson from 2001. So this reference here is just telling you sort of the authors that found this determinantal structure. And these references here are those who were able to obtain local edge asymptotics. And it's very non-exhaustive. You could also upgrade the assumption of A being GUE to A being Wigner. This was due to Lee and Schnelli. But the main takeaway that the main thing I want to convey here is that there really aren't results for local edge asymptotics, where A and B, these summands, are more general. There is one sort of exception in this direction for bulk universality. So Che and Landon in 2019 were able to show that for general AB under some regularity assumptions has the bulk can be described by the sign process. So this is a very sort of rough list of things that are related to this direction. Okay, so for us, we'll simplify the setting for the purposes of this talk. We'll just consider the A1 through AKs to be IID. And so these A1 through AK, recall, are the random matrices. And V1 through VK, the representations, are all just going to be isomorphic irreps of UN. Okay, so let me just define quickly a notion of convergence here. So we want a notion of convergence that's stronger than just weak convergence. We want to prevent outliers. We want to prevent particles from escaping to infinity or being somewhat pathological, but at a local level, but sort of, in a way where that pathology is invisible at the global level. So we'll assume that mu n converges, I'll say converges with its support to mu, and denote it as written in blue, if the mu n's converge to mu weakly, and we have the following convergence as n tends to infinity, that the supremum of the distance between particles in mu n, or x in the support of mu n and y in the support of mu, tends to 0. And so this is really just capturing the notion that we're not allowing these two measures to really have too much outside of its overlap. Okay, so I'm going to pause here and see if there are any questions so far about this notion. Okay, so
sorry,
here's
your second condition on the support seems very strong. Like if you just had the support of both being an interval from 0 to 1.
Mm-hmm. Right. So
then wouldn't I just have that supremum is equal to 1 if they have the same support? Why is this good as
I'm missing an inf. I apologize. There should be an inf here. Hold on. So yeah, there's definitely something wrong with this statement as written. Right. So really what I want to say is that the distance, so this was me being a little lazy, so I apologize for that. But really what I want to say is here mu n should be some sort of empirical distribution on particles. So this is a little painful right now because of what I'm using. Oh boy. Okay, so we have a sum and we have this delta Li. And what we want is we want the distance. Oh man. Distance.
You're saying distance from Li to the support of mu?
Exactly.
Okay. And you just want that to go to 0.
Yeah. So yeah, this is definitely wrong. I think trying to write this a little too abstractly was not worth it and wrong. Okay, so yeah, so basically the soup should be over sort of these particles Li, and this should be tending to 0. Oh boy. Thanks for pointing that out, Mark, by the way.
We should think of this convergence from point measures to another.
That's
value.
right.
Okay.
Yeah. Okay, so this is, all right. So I apologize for that. So if I press this button, I think it'll take me to the very beginning. So perhaps I'll just leave it. Okay, so hopefully, you know, this is clear now. The first theorem I want to state then is in the random matrix setting. So we'll have some explicit constants tau mu and tau sub q mu, such as the following holds. So if k, the number of summands, is a fixed number which is larger than tau mu, if we also assume that each of these AI, so recall they're all IID now, so if mu A1 converges with its support to mu as n tends to infinity, and if the eigenvalues of the sum of the AIs are denoted by x1 through xn, then rescaling by this n to the 2/3, subtracting out by these explicit constants. They're not so important here, but the point is this fractor E is supposed to be the edge, and V is going to be some variance parameter. This should converge to the Airy point process as n tends to infinity. Okay, so if you have enough summands, if you have IID sums, and the number of summands k is large enough but finite, then you will see the Airy point process at the edge. This tau mu, by the way, so I haven't written out what it is, but it's given in terms of the Cauchy transform of mu. And so there's an explicit formula for it. The second statement is an analogous statement in the world of these quantized models. So now again, we choose k to be larger than a slightly different threshold tau q, which again is given by the Cauchy transform of mu, but it'll be sort of different. And we assume again that these spectral measures, where the tuning parameter, if you recall, is epsilon equals 1/n, tends to mu with its support as n tends to infinity. Then, if we take the signature lambda distributed by this row V1 tensor up to Vk, the particle system associated to lambda, so the particle system meaning, you know, this sort of lambda I plus n minus I over n, will converge in the same way as above to the Airy point process as n tends to infinity. Okay, so this is really sort of the analogous theorem as above. So any questions about this statement?
Why do you need the thresholds?
The threshold? Because if mu is a highly pathological limiting measure, you shouldn't expect there to be the Airy point process. So if k is, say, like small. So for example, if mu is something like a Rademacher distribution, if mu has delta mass, you know, has mass 1/2 at -1 and 1/2 at 1, then when you take k equals 2, if you take the sum of A1 plus A2, the limiting distribution is the arcsine law. And so this doesn't even have square root decay at the edge of the support. And so this is, you know, the right scaling there, you know, things are going to be like on the scale of like 1/n squared at the edge there. And you really don't expect to see the Airy point process.
Mm-hmm.
Yeah, it's a great question. So actually, let me just explain a little further why we would think that if we, you know, take k large enough that the Airy point process should even appear, considering we can have some pretty pathological limiting measures mu. So here's a heuristic. Okay, so this is, I do want to get rid of this so you could see the title. So here's a heuristic. So let's first think of the matrix size as fixed. So before I actually say this heuristic, let me just say that for the remainder of this talk, let's just sort of focus on explaining this result, the first one, the random matrix result. So let's suppose n is fixed, the size of the matrix, and let's see what happens if we let k, the number of summands, tend to infinity. So you have a bunch of IID copies of A1. So you have A1 through AK. And so if you look at taking a sum A1 to AK, you can expect that you can, entry-wise do some CLT, central limit theorem, classical central limit theorem. Moreover, if you're keeping n fixed, you can think of the vector, this n by n vector, or this n squared vector of all of its entries as converging, to some Gaussian vector, n squared Gaussian vector with some covariances. So this is basically what I'm saying is that you can expect that the sum A1 through AK upon translation and renormalizing properly should look Gaussian, and the covariances you could work out explicitly, and this was done by Gorin and Sun in I think their appendix. And you'll find that if you take the following limit, so we just take the sum of the AIs, subtract out by this scalar matrix in terms of the trace of A1, and rescale by 1 over square root k, then this should converge as k tends to infinity. Again, the number of summands is increasing to infinity, but the size is fixed. Size of the matrix is fixed. This should converge to the following. So here you can think of this as some constant. Since n is fixed, sigma n is just the variance, sigma n squared is just the variance of mu A1, times yn, which is a GUE, minus some random scalar matrix. And the scalar is given by 1 over n times the trace of yn. So this term here in the parentheses is, I think Gorin and Sun refer to it as the traceless GUE, and you can check that the trace of this thing has to be 0. And so you can see that, by sort of a simple application of central limit theorem and working out the covariances, this is what the limit should be. And so returning, in our setting now, we had this sort of flipped. We had k fixed and n large. So let's try to, work our way towards that heuristically. So now the above, by sending n to infinity in the above here, it'll turn out that this scalar term here will be negligible for n large. And this will give us the following heuristic. So if k is much, much larger than n is much, much larger than 1, then the sum of the AIs will look like some scalar term depending on k and n, plus some, some number times a GUE. So in other words, the sum of the AIs look like, some translation plus a dilation of a GUE. And so we might expect then that for under this regime where both k and n are very large, that the distribution at the edge should look like the Airy point process. It should match that of the GUE. So these results from before, you can sort of interpret as capturing this. But really, it also sort of says you don't need to take k to infinity. Alternatively said, you can think that this heuristic just tells you that as we increase k, this is sort of increasing the regularity in these sums, no matter how pathological your original AIs were. And so if we take k large enough, and it turns out that k, taking k large enough means you can still take k to be finite, then you should see GUE statistics at the edge. So are there any questions about this heuristic? Okay, cool. So now that I've sort of stated the results and given some idea of why you might expect it to be true, let me give you just a sense of the ideas behind the proof. So typically when a lot of integrable models, the approach is to, there are a lot of integrable models where the proof to showing convergence to the Airy point process uses correlation kernels. This is certainly not the only way to do it and not the only way it's been done. But for, at least on the side of random matrices, this is sort of widespread for integrable models. So the approach that we'll take will be a little different. There's no determinantal structure in general for these additive models. And so you want to appeal to something else. And what we'll use is an approach based on showing convergence of these exponential moments. So let me just outline that a little more. So suppose you have eigenvalues x1 through xn. And let's say we know, I know this is a bit backwards, but let's say we know that we have convergence to the Airy point process, right? So we have some constants, you know, fractor E and fractor V, such that this convergence happens as n tends to infinity. So if we know this, then what we can do is the following. So let's say c greater than 0 is fixed, and these lowercase fractor a1, a2 denote an Airy point process. Okay, then if I take the following expectation, so this is some expectation over the exponential moments of these xi's. Then if I rescale, or if we have this parameter n to the, you know, if we have this Laplace parameter given by n to the 2/3, or growing of order n to the 2/3, then this should behave for n large like e to the n to the 2/3 times the edge, expectation of, you know, some exponential moment of the Airy point process. So this part here follows directly from this assumption above. Okay, so if we know that the x's converge to the Airy point process upon this rescaling, then we should see this convergence, or this sort of asymptotic behavior. And there's a more general statement, so you can take joint exponential moments instead of just single exponential moments, and there'll be some statement that tells you, you know, that taking the appropriate expectation, tuning the parameters by n to the 2/3, should behave like sort of the corresponding thing on the side of the Airy point process. And it turns out that if you, you know, sort of write down these statements for all the joint exponential moments, then this also, you know, if instead you had this second part here, if you had convergence or this asymptotic behavior, as n tends to infinity for all joint exponential moments, then this implies this first bullet here. So what I'm trying to say is that these two statements are sort of equivalent to one another. Which is what I'm saying here. So any questions about that? Hopefully I've conveyed that clearly. So the thing I want you to take away from this slide is that if you have suitable analyzable formulas for these exponential moments of the x's, then by taking the appropriate limit, you can prove convergence to the Airy point process. So this leads us to asking, okay, well, we're going to take this approach. So how do we obtain the exponential moment formulas for these additive random matrix models? So for this, we use the formalism of multivariate Bessel generating functions. So this is sort of a big word, and I'm probably just going to refer to it as an MBGF from now on. But really, the way you should think about this is as some analog of the characteristic function in this random matrix world. So let me just define this object. So here's what it is. If you have an n vector, n vector of real numbers x1 through xn, then the multivariate Bessel function is the following. We'll denote it by mathcal. B sub x is the function in z1 through zn, and it's just going to be an integral over the unitary group. And here, the measure which we're integrating with respect to is the Haar measure on u. And the integrand here is just e to the trace x u z u star, where x is going to be a diagonal matrix with the x's as its entries, and z is a diagonal matrix with the z's as its entries. Okay, so this sort of looks like a matrix characteristic function or Laplace transform. And you can alternatively, there's another perspective where if you're familiar with Schur functions, this is some continuous analog of the Schur functions. And that's actually where this, we're able to apply sort of this approach to the quantized setting as well. Okay, so we want to define the multivariate Bessel generating function. So the MBGF of X, which is a random Hermitian matrix with eigenvalues X, is just this phi X Z1 through Zn expectation of a normalized multivariate Bessel function. Okay, so this expectation is over the random eigenvalues X, and then this thing will be a function of the Z's. Okay, so I'll pause just for a couple seconds here so you can absorb this a bit. Okay. So let me give some examples of MBGFs. So if X is a GUE matrix, then you can compute that the MBGF of X is just a product of e to the zi squared over 2. So this, degenerates well in the case when n equals 1 to the Laplace transform. Right, so this is pretty simple. Another simple example is if A is deterministic. So if A has deterministic eigenvalues A1 through AN, then the MBGF of A is just given by a multivariate, normalized multivariate Bessel function. So this sort of comes directly from the definition that we have here. I shouldn't be going back and forth, but it comes directly from this definition here, because if A has deterministic eigenvalues, then your expectation is just a delta mass at A. And finally, the third property, or third example I want to go through is one that shows that this is, very similar to the Laplace transform or characteristic function from classical probability. So if you have A and B are independent random unitarily invariant Hermitian matrices, and I take, and I want to know what the MBGF of A plus B is, turns out these two things, it just factors into the MBGFs of A and the MBGF of B. Okay, so hopefully I've convinced you that this is a nice object. So how are we going to use this? So the goal was to, get some exponential moments, formulas or useful representations for the exponential moments of these random matrices. So here's sort of the first, statement in this direction. So let's say X is some random Hermitian matrix with eigenvalues X1 through Xn. So now this is not a direct statement from Borodin Corwin, but it's sort of implied by some of the results in that paper. So if you assume that the MBGF of X has this product structure, so it just sort of splits into product of I from I equals 1 to n of f of zi for some function f, then you have the following representation for the exponential moments of the x's. Okay, so it's just some simple formula which is just in terms of this phi x through the f's, little f's. So for example, we had if x is GUE, then f of x is e to the x squared. So this gives you a formula for the exponential moments of the GUE. More generally, this is not the structure that you'll see for these additive random matrix models. So you need something more in order to study these additive random matrix models. And so this is given by the following proposition. So more generally, we have the following, that if you can find some function phi tilde x, so this phi tilde x is going to be a lift of this phi x. And in what sense do I mean this? So phi tilde x is going to be a function in n+2 variables. It'll be a function of z1 through zn+1 and w. It'll be symmetric in the z's. And the reason why I'm using this backslash is there's a it's not a quotient, it's not zn+1 by w. This is really to separate the z's and the w, and the reason for this notation has to do with its connections to these things called supersymmetric Schur functions, which are which is like, this is the standard notation for them. So if you can find such a function that has the following property, that if you take Zn plus 1 equal to W, then these two variables sort of cancel and you end up with phi x Z1 through Zn, then the exponential moments of the x's are given by the following contour integral formula in terms of these phi tildes. So this phi tilde is we call a supersymmetric lift of phi, and there's definitely not enough time for me to explain why it's called that. But this is sort of the entryway into these results about the additive random matrix models. So are there sort of any questions at this point about the statements or anything else?
Do you have any intuition on why you take all of you take the first n variables to be 0?
Oh, so yeah, so this is related to the fact that here we're looking at a multivariate Bessel function, which is normalized at the zeros. So somehow, with a lot of these integrable models, there's some right way to normalize these things. And it turns out that for the additive random matrix class, this is the right way to be normalizing these objects. This is a very sort of, weak answer, but roughly that's why the zeros are there. Any other questions? Yeah, so these zeros really you can think of as corresponding to the normalization variables. So let me try to give some further explanation to this, how this result sort of degenerates to this result here from Board and Corwin. Okay, so let's see that this happens. So if phi x Z1 through Zn has this multiplicative form, then you can check that a lift, a supersymmetric lift of this phi x is given by the following. So if I take phi tilde x, Z1 through Zn plus 1, W, then all I need to do is take 1 over f of W times a product of the f of zi's over I equals 1 to n plus 1. So if I do that, you can see that by setting Zn plus 1 equal to W, you will just have cancellation. So for these multiplicative functions, it's pretty simple. Okay, so if we set the first n variables to be 0 now, and Zn plus 1 to be Z, you'll find that this equals f of Z over f of W. The reason why is that f of 0 has to be 1. This comes from the fact that if you look at the definition of a multivariate Bessel generating function, if you evaluate it at zi's equals 0, this should give you 1. So now if we take this and input this into our formula that we had in the previous proposition, right? So we have phi tilde x 0, 0, 0, z plus t, z. Then we just recover the statement of Boarding Corwin. This is so it really does properly degenerate to that result. So now we see, okay, well, right. So you can show that you can say that if there exists some phi tilde, then you have this formula. And for when phi is multiplicative, has this multiplicative form, you're able to say phi tilde equals this thing. Okay, but unless you can say something about phi tilde for more general functions, this is a pretty useless formula. And it's true that for general phi x, it's not going to be easy to find a supersymmetric lift. However, it is the case that if phi sub a has this is equal to a normalized multivariate Bessel function, so this is in the case, this was, recall from our examples, what the MBGF is for A with deterministic eigenvalues, then we can find supersymmetric lifts for these families. Okay, and so, right, so we're able to get supersymmetric lift for these deterministic matrices. What about these sums? So recall that we have this factorization property, that if you have independent A and B, then the MBGF of A plus B will just factor into the MBGFs of A and B. A supersymmetric lift of phi A plus B is just equal to a supersymmetric lift of A times a supersymmetric lift of B. All right, so here just a lift of a product is product of its lifts. And so if you can find supersymmetric lifts for these multivariate Bessel functions, then, okay, that should not be going off. Right, that's absolutely bad timing. So if you can find supersymmetric lifts for these multivariate Bessel functions, then you can get supersymmetric lifts for sums of these, or these additive random matrix models, just by taking products of lifts that you get for the multivariate Bessel functions. And then you have these exponential moment formulas. You have some suitable representation for them, and now you just take asymptotic. So you hope that these formulas are that you can take reasonable asymptotics for it, and this will give you the local theorems by the sort of explanation that I gave before. So this is roughly the outline of how we are able to show that the Airy point process appears in these random matrix limits. But I should also say, that this method seems like it should be able to access other limits where, you might not have the Airy point process. So this is basically what I wanted to say about this. But let me just sort of summarize. So the main result that I shared, in the second half of this talk is that you see the Airy point process appear in a regime where the number of summands for these IID matrices A sub I is large enough, but a fixed number. And then there's some analog in the quantized case where you replace sums with tensor products. And our approach is based on the moments method and using these multivariate Bessel functions. And the key input that we have is this formalism of supersymmetric lifts, and the fact that we're able to find formulas for lifts of multivariate Bessel functions, which I didn't really show you. But this is sort of the picture of what's going on. So this is all I wanted to say.
Okay, thanks Andrew for the talk. So if anyone has questions, they can unmute themselves and ask. So I have a question, like about these origins about the supersymmetric lifts. Are they coming from the quantized analogues?
It's not super clear where they're coming from. So like you can sort of view them as coming straight from the random matrix models. Like you don't need to sort of pass through the degeneration of quantized models to see this supersymmetric lift.
Mm-hmm.
Yeah. But in the case of these quantized models, you replace these multivariate Bessel functions with Schur functions, and a supersymmetric lift of a Schur function turns out to be exactly something called a supersymmetric Schur function. And these things, were studied by, several people before, and this is like certainly an entry point to understanding these models from that direction. But I wouldn't be able to say that supersymmetric lifts for these random matrix models come from the quantized models.
Andrew,
yeah.
So these multivariate Bessel functions, so presumably when you have one variable, it just becomes a standard Bessel function or of one type? Or what's Bessel about these?
That's honestly, I should know the answer to that question, but I don't think that's the case.
Why are they
You
called
really
Bessel?
just get, what was that?
Why are they called multivariate Bessel functions?
That's a great question. I should know the answer to this. Really, to me, I'm less focused on, I would say that I'm sort of just passing on the nomenclature, but really I think of these things as these sort of matrix integrals.
But is that, if you take n equals 1, so now you're just integrating, I guess, around a circle or something? And
yeah.
so this is some pretty basic integral.
Yeah. It should just, yeah, I mean, it's really just going to degenerate to like e to the xz in that case.
Well, it's a little, it's, if you think of it as indexed by the angle, it's something a little bit more complicated than that, right? It's e to the I theta, right?
So I think that this sort of conjugation by the u's, it'll just become commutative when n equals 1.
Yeah. So just the Fourier transform.
Exactly.
Actually, it's not even there.
I mean, it's a Laplace transform really for,
Well, it's not a transform at all. It's just e to the xz. It's what you said, right?
Yeah, so the multivariate Bessel function just becomes e to the xz, but the generating function becomes the Laplace transform.
Mm-hmm. So who introduced the terminology multivariate Bessel function?
I think the furthest I've gone back in terms of the literature is either Vadim, is either Yi Sun, or, sort of going back before then, there's some references that Yi Sun has, but I'm not sure if,
Okay. Well, if he comes to the group meeting this afternoon, we can ask him.
Yeah. Yeah, I mean, this is definitely something that's bothered me, but, I certainly should have looked into it further upon being bothered by it.
Maybe when n equals 2, it somehow relates to a Bessel function or something.
Maybe.
Okay.
Like, it looks to me just the moment generating functions for the random matrices, to be honest.
Yeah. I mean, I would probably prefer to call it, like a continuous Schur function, or, I'd prefer to call this thing like a matrix Laplace transform.
Mm-hmm.
But, there's existing names for it, so.
Potentially quite dumb question. In the multivariate Bessel function, this thing ends up working really well with sums of unitarily invariant matrices, and it's written as like an integral over u of some like unitary conjugation of some function. Is it, if you look at other things like orthogonally invariant matrices, taking sums of those or something, can you write something similar where you just replace u with o everywhere, and maybe tweak it a little bit, or
yeah, you can
still behave well under sums?
So you can do that, and yeah, the fact that it behaves well under sum is just like, you can check that when you take bx times by, that like, you can pull the sort of integrals
from this integral.
Yeah.
Okay.
But the problem is, so one thing that really helps in the multivariate, in this unitary case, is that this has a nice form due to Harish-Chandra, Itzikson, and Zubair, where it's just equal to a quotient of some determinant divided by a Vandermonde. And you could sort of realize from that, for example, that it is a limit of Schur functions. And that sort of explicit form is one thing that helps in our case. Like, from the explicit form, we're able to find an expression for its supersymmetric lift.
Okay, so what you're saying is basically, if you wanted it to be invariant under, say, orthogonal, you could write down a similar formula where you place u with o, but we don't have a nice way to evaluate it.
I can't say we don't have a nice way to evaluate it. Certainly people have like expansions for this thing, but I don't know of a way to get a useful expression for it, at least to work in this framework.
Okay, useful expression to get this sort of supersymmetric lifts you're talking about.
Yep.
Okay.
I found another usage of the term multivariate Bessel function, which I think is different. Actually, it seems to. So is this multivariate or multivariable?
I've only seen multivariate.
Okay. So then it's fine, right? Because in other literature, they use multivariable Bessel function.
I see. Yeah, I mean, there are really only sort of two places I've gone back in the literature for this, or three places. And this is, a paper of Vadim, of Gorn and Sun, and a paper of Gorn and Marcus, and a paper of just Yi Sun alone. So this is sort of.
But these are, so just to make sure I understand, so these are just limits of sure generating functions.
That's exactly what they are, yeah.
Okay.
Yeah, perhaps this sort of matrix integral form makes that much less clear. But somehow on
the same as these sort of continuous sure functions, right?
That's exactly what they are, yeah.
Oh, okay. Oh,
yeah.
that's good to know.
Yeah.